Hello everybody. In this video, I want to talk about one final element of hypothesis testing. Now, so far we've been looking at hypothesis testing where we have a single sample and we're trying to compare the sample average with the population average and trying to gauge if we can make statements about the population mean from the sample mean. So that is the case of a one sample t-test. Now, this process of hypothesis testing is so versatile that it allows us to do so much more than just a single sample t-test. Now, the particular scenario we learn of in this video is this situation where one would guess that maybe the population mean is different in different groups of people. For example, if we are looking at, say, the test scores of students, for some reason, we may expect that boys may score differently compared to girls. So, where in the population of people, we are talking about the case where the population mean for boys could be different from the population mean for girls. So, if we are interested in checking if a statement like that about a population parameter is true or not, we could use the principles of hypothesis testing to examine those conditions also. So right now, we're going to look at the scenario where we're going to try and make comparisons between the measurements that have been taken from two different groups. So think of scores from boys versus scores from girls, or you could think of scores from young children versus scores from older children. Okay. Now we're looking at checking if there is any difference between those two groups in the population. And we could actually use similar principles to do that. We could use similar principles of hypothesis testing to look for evidence in our sample to suggest whether the population statement is true or not. Now we'll use this similar process, and there are only going to be two major differences. The first is in how we set up the hypothesis. Earlier, we were writing down our null hypothesis that mu is equal to mu naught. That is, a population mean is some value, and then that value could be anything. Right now, because our interest is in comparing two means, so we'll only look at comparison between two means. That's the focus in this course. So when we are trying to compare two means, we'll define the null to be that there is no difference between the two means. Okay. So earlier the null was that population mean is equal to some value. Right now we are interested in the difference between two population values, okay, or rather difference in the means between two groups. So we're going to redefine the null that there is no difference between the two groups. And how will we formally write this down? If the mean of group 1 is referred to as mu1, and if the mean of group 2 is mu2, our null hypothesis will be that the two means are equal to each other. That is the status quo we are defining. There is no difference between the groups, they're equal to each other. And we'll write down our null as mu1 is equal to mu2. In other words, mu1 minus mu2 is equal to 0. There is no difference between the two means. So that's how we'll set up our null hypothesis. Now, in this course, we'll focus specifically on the case where there is no difference between the two means. That will be our null hypothesis. But in more advanced situations, you could use the similar processes to look at non-zero differences also in your null hypothesis. But we'll ignore that for now. So that's one difference, how we set up the null. The second, naturally, is that our test statistic is going to be computed differently. Test statistic meaning our z star and t star, where we did x bar minus mu by s over root n, right? That's our test statistic. And that's naturally going to be computed differently. Now, earlier, when we were talking about mu and x bar, and we were trying to see whether x bar is close to mu or not, what we did was we came up with the sampling distribution of x bar. And we figured out whether a particular x bar value is very likely or very unlikely to show up in relation to the mean, which is the central value. So in order to be able to write down the test statistic, what we had to do was first have the sampling distribution of x bar. Well, right now, if we are interested in talking about h naught is where mu1 minus mu2 is equal to 0, where you're looking at the difference between the two means, A natural starting point is to look at the difference between your sample means. Natural starting point is to look at x1 bar minus x2 bar. So just like how we looked at x bar for mu, if we are looking at difference between mu1 and mu2, and if we are trying to find out whether our sample is giving us evidence to believe in that null or not, we have to have a starting point. And the difference between sample averages between those same groups could be a good starting point. If you are interested in, say, the difference in population level scores between boys and girls, maybe you've taken a sample of boys and a sample of girls, and you could compare the average from each of those samples. That's a good starting point. So earlier, when you had x bar for mu, we were able to write down the distribution of x bar using the central limit theorem. We were able to write down that x bar is normally distributed with mu and sigma square n variance, sigma square by n variance. Now, if we were to do something similar in this case, we'll have to figure out how to write down the distribution for x1 bar minus x2 bar. So to compare the difference between the two means, we have to use x1 bar minus x2 bar, and we need to write down the sampling distribution of x1 bar minus x2 bar. But it turns out that the central limit theorem actually helps us do that too. Now, once you're able to use central limit theorem, then everything flows smoothly. It's the same logic where you're able to draw a normal bell curve, and once you identify the tails as areas with least low probability, then you have your rejection regions. But now the distribution in question has to be for x1 bar minus x2 bar. So we have to find the mean and variance of that distribution, and the central limit theorem comes into our rescue. Turns out that if you have two random variables, say x1 and x2, okay, if you focus only on the random variable x1, whether if it comes from a normal distribution with these parameters, or whether the sample size is greater, if the sample size is greater than 30, we could write down that the average x1 bar will have a normal distribution with the same mean as the parent and a sigma square 1 by n1 as its variance. Okay, so suppose random variable, the population random variable is x1, and that is normally distributed with mean mu1 and sigma square 1 variance. If either the parent is normally distributed or we know the sample size is greater than or equal to 30, we can use central limit theorem to identify sampling distribution of the sample mean for that variable. Similarly, given another parent distribution x2, we could also write down the distributional expression for x2 bar. Now, turns out that if x1 bar and x2 bar are actually independent, then we could actually write down the distributional function for the difference between these two sample means. Remember, x1 bar is also the sample mean for x1, x2 bar is the sample mean for x2. And once you know the distributions for these two random variables, you can write that down using CLT. And CLT tells us that the difference in sample means also has a normal distribution, such that this distribution of x1 bar minus x2 bar has a mean that is equal to the difference in the population means and a variance that is equal to the sum of the individual variances. So take a minute to memorize this statement. X1 bar minus x2 bar will have a normal distribution. So just focus on these two and this statement. When you do x1 bar minus x2 bar, that has a normal distribution with mu1 minus mu2 as the mean. But the variance is a little different. We add the two variances together, and that will be the variance for x1 bar minus x2 bar. And now once you're able to write down the difference in means as a normal distribution, then we can immediately calculate our test statistic. It will be Z star, where you're taking the random variable, subtracting the mean of that random variable. In this case, you're actually taking the specific values of x1 bar minus x2 bar. You subtract the hypothesized mu1 minus mu2, and you divide by the standard deviation. And then that's how you get your test statistic. And now this is very similar to how we did x bar minus mu by sigma by root n earlier, when we knew X bar was normally distributed with mu and sigma square by invariance. It's a very similar story here, except that you are looking at the difference in means, that is it. And once you look at the difference in means, naturally the population mean will vary and the variance will also vary. This is all there is to a two-sample hypothesis testing. Now, when we don't know sigma, we end up using S1 instead, and S1 and S2 instead. And instead of a Z star, we'll call it a T-score, where it will be a T distribution. And using a T table, we can find out what the probabilities are. And given that we are focusing on this situation where mu1 is equal to mu2 in the null, that is mu1 minus mu2 is equal to 0, your test statistic will essentially collapse to x1 bar minus x2 bar divided by this, this expression. And this follows a T distribution. And we can construct a confidence interval. And it essentially proceeds in much the same way as our single sample hypothesis testing, except that, earlier we were looking at this distribution where you were looking at sampling distribution X bar where the center was at mu naught. Now we'll be focusing on the sampling distribution of X1 bar minus X2 bar where the center is at 0. And the 0 is mu1 minus mu2 is equal to 0. And that is all the differences. If you find you'll define rejection regions in much the same way. So suppose you find a rejection region there, and if you happen to find your test statistic falling into the rejection region, then that is proof that your test statistic is very different from 0. And if your test statistic is very different from 0, it means that mu1 minus mu2 is not 0, or in other words, mu1 is not equal to mu2. So if you reject the null that mu1 is equal to mu2, or if you reject the null that mu1 minus mu2 is 0, then mu1 is not equal to mu2. That there is a significant difference between the population means. That will be your conclusion. There is a significant difference between the means of the two groups. That's your conclusion. Now, I've shown you the example when for a two-sided test, we could use a one-sided test here as well. The application is exactly the same. The only difference is how you're defining your null and alternative hypothesis and how you're thereby calculating your test statistic. You just have to remember to interpret everything in relation to the null. So here, a significant value here in the rejection regions will tell you that the difference in means between the two groups is very different from 0. If the difference in means is different from 0, then it means that the means are not equal to each other. And therefore, you reject the null that the means are equal to each other, and you say that there is a significant difference between the two means. And that will be your conclusion. So this is a very powerful concept which is very frequently used in real life scenarios. And what makes it even more attractive is that it's super easy to do this in Excel and R, and all you need to do is just type in one single function and it will spit out the results for you. You don't have to manually calculate anything. So the only thing to remember here is that when you compute this test statistic, finding out the degrees of freedom is a little bit cumbersome in this case. So solving these problems manually requires more nuance, and it's a bit more advanced for this course. So we'll use Excel and R to solve these types of two-sample t-test problems. So I'll do a couple of examples in the next video. I'll see you there.